Hello everyone, welcome to another episode of Math-321. So this is actually going to be the last episode of Math-321. So I was thinking of doing like a summary of Investigation 32 and 33, which contains some pretty important topics for group theory. But I've decided I want to just give you guys some more time to work on homework and catching up on things. So this will be our last lesson today, and then Friday will just be a work day. So we're going to finish up Investigation 31 today, and again, just like last time, I'm not going to fully go into the details of everything. I'm going to skip over some activities and some proofs and things, but I'll just go over the main ideas. Okay, so here are the important things from last time. We have definition 31.2. So a P group, where P is a prime, is a group whose order is a power of P. So like, for example, a group of order 8 would be 2 cubed, so that's a P group. And then we had Theorem 31.3, let P be a prime, and let G be a finite abelian P group. Let A in G be an element of maximal order in G. Then there exists a subgroup K of G, so that G equals the internal direct product of the cyclic subgroup generated by A times K. And then just note that part of the definition of that internal direct product is that that cyclic subgroup generated by A and K only have the element of the identity in common. So otherwise they are disjoint. And then we had a corollary from that, where we proved actually in an activity that we have corollary 31.6, which is let P be a prime and G a finite abelian P group. Then G is an internal direct product of cyclic P groups. So basically you can keep applying Theorem 31.3 to the subgroup K, and you can keep breaking it down into smaller and smaller cyclic subgroups like A, but using different elements. Okay, so let's keep going from there. So we're going to go over an example now of how to use corollary 31.6. So we're going to determine all abelian groups of order 8, and 8 of course is a power of a prime too. So let G be an abelian group of order 8, and 8 here is equal to 2 cubed. So by corollary 31.6, we know that G is isomorphic to a direct product of cyclic P groups for P equals 2. So the only possibilities for that are that we're going to get either Z8, so that is a group of order 8, or we're going to get the external direct product of Z4 with Z2, so that would also be a group of order 8. Or we can do the external direct product of Z2, Z2, and Z2 again. So that is also a group of order 8. So why do we only need to use these Z groups? That is because we know that we can break up G into a product of cyclic groups, and every cyclic group is isomorphic to one of the Zn groups. Sorry, every abelian cyclic group. Well, actually, no, I take that back. I guess all cyclic groups are abelian, aren't they? Since they're products of they're powers of a single element. Yeah, so we only need these Zn groups if we know that our P groups are going to be cyclic. Anyway, so since Z8 contains one element of order 2, Z4, the external direct product of Z4 and Z2 contains 3 elements of order 2, and then the external direct product of Z2, Z2, and Z2, that contains 7 elements of order 2. That means that these 3 groups here are not isomorphic to each other, because remember, the number of elements of each order is one of those invariants that you can use to show that groups are not isomorphic. Okay, so none of those 3 will be isomorphic to each other. So that means there are exactly 3 abelian groups of order 8 up to isomorphism. So that's quite interesting actually, and it's not, it wouldn't be that difficult in any case to use a computer or something to figure out all the different groups of order 8, just like making all the different possible operation tables. But certainly when you're using a higher order, then it would be extremely difficult to figure this out otherwise. So now let's talk for a minute about integer partitions. So an interesting question to ask is, given a prime power q to the n, so q is our prime here, how many isomorphism classes are there of finite abelian groups of order q to the n? Like, is there a formula for this? And the reason we're switching to using q as our prime here instead of p will become clear in just a second, because we're going to use p to stand for something else on this slide as well. So the answer is connected to integer partitions. So an integer partition, this is like a topic that would be in like a discrete math class or something. But anyway, an integer partition of a positive integer n is a non-increasing sequence of positive integers whose sum is n. So to illustrate, for example, all of the integer partitions of 4 are the following. So you can just have 4 by itself, or you can have 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. So that is all the different ways of breaking up 4 into a sum of numbers, positive numbers. So there's actually a function called p of n, that is the integer partition function, and that is the number of partitions of the positive integer n. And I believe, I can't remember if there's a closed formula for it or not. There's certainly a recursive formula. So for example, p of 4, the number of different ways of writing 4 is 5. We just showed the 5 ways right there. And if you want to read more about that, I suggest go to the online the online encyclopedia of integer sequences, and this is sequence number A000041. If you guys have never been to the online encyclopedia of integer sequences before, it's quite an interesting website. It's kind of an old website, so it's a little bit clunky looking, but it has just tons of incredibly great, fascinating mathematical information on there, and that is a place where all of the different interesting and useful and known and named integer sequences live at. So you can read up on it there, or of course that Wikipedia, they have a page on it as well. So anyway, why are we talking about these integer partitions? Well, these partitions of 4 actually correspond to all of the different finite abelian groups of order q to the 4. So let's look at the table on the next slide that will show you that. Okay, so let's look at the example for 4 here. So you see there is all of the different partitions of 4, and those actually correspond over here to all of the different ways of having a finite abelian group of order q to the 4, because those are the different ways that you can break up that 4 exponent, and then you can break down the group into those different factors like that. Okay, so this integer partition function, it actually gives you all of the different isomorphism classes of groups of order q to the n. So that's quite interesting. And this might come in handy for you on that final exam problem. You'll need this technique, and then also there's another example later on I'll show you that you'll also need. Okay, so let's do a preview activity here to get us in the right mindset for the next concept. So go ahead and pause the slide and give this preview activity a try, and then I'll go over it. Okay, so let's go over this. So G is U28, and U28 is the group of units in Z28 under multiplication, and then the orders of all of those elements are shown in the table above. So let G2, or G of 2, be the subset of G consisting of the elements whose orders are powers of 2, and find the elements of G of 2. Okay, so right at the beginning you might make a mistake because 1 is actually one of these elements, and that is because the order of 1 is 1, which is 2 to the 0. Okay, so you do need to include 1. And then, of course, there's also 13, 15, and then 27 are the other ones. And that's it. And then for G of 3, we're doing the same thing, but for powers of 2, so we're also going to have 1, because that's 3 to the 0. And then we're going to have 9 and 25. Okay, and then part C are G of 2 and G of 3 subgroups of G. Explain. So obviously we have the identity, but we need to check whether it's closed and whether it contains inverses. So to check whether it's closed, let's check what 9 times 9 is. So that is actually mod 28. It is actually 25. And then let's check what 25 times 25 is. So that one is actually 9, and then we need to check 9 times 25. And that one is actually 1. So yes, it's closed, and also it contains inverses because 9 and 25 are each other's inverse. So yeah, that one is a subgroup. All right. right, and then G of 3. Oh, so this was for G of 2. So for G of 3, I needed a little more room than this, sorry. So for G of 3, 13 times 13 is 1, so that is its own inverse, and then 15 times 15 is also 1, so that is its own inverse as well. And then 27 times 27 is also 1, so that's, we got the inverses, and then I just need to check 3 more things to see if it's closed. Checking the multiples of these against each other. Oops, sorry, that's supposed to say 1. Oops. Oh, now my pen doesn't want to erase. So 27 times 13 is 15. 27 times 15 is 13, and then finally 13 times 15 is 27. And I was just using Wolfram Alpha to do those mod operations there. Okay, so yes, that one is also a group. All right, this is really messy here. Okay, so what group is G2 times G3? So this is the internal direct product. Okay, so we just multiply all the elements in G2 times all the elements in G3 and then see what we get. So I'm really squished here, but sorry. So 13 times 9, that is going to give us 5. 13 times 25 is going to give us 17, and then 15 times 9 will give us 23, and then 15 times 25 will give us 11. 27 times 9 will be 13, and then 27 times 25, which is the last one, will be 3. Okay, so all of that means that G2 times G3, that is actually the entire group U28. Okay. Okay, so now let's look ahead to what we're going to try to do for the rest of this section, which is not very much longer, but I just want to kind of try to put this all together. So far we have that we can write a P group, a group that has a power of a prime as its order. We can write that as a product of cyclic groups, and now we're going to try to extend that to all finite abelian groups. And we're going to be using P groups as our building blocks. So we saw in the last activity that we were able to break down a group of order 12 into one group that was all the elements of power 2, and then the other group that was all the elements of an order that was a power of 3. So we're going to do the same thing for all groups that are finite and abelian. So let G be a finite abelian group of order n. By the fundamental theorem of arithmetic, we can find distinct primes p1, p2, ... up through pk. So in the last activity, those were 2 and 3. And we can find positive integers m1, m2, up through mk, so that n equals p1 to the m1, p2 to m2, and then so on and so forth up through pk to mk. And then what we're going to do is we will show that we can break G up into an internal direct product of P groups. Remember, those are just groups that have the order being a power of P. Okay, we're going to break those up. We're going to break G up into an internal direct product of P groups, and those P groups are going to be G of P1, G of P2, ... and so on and so forth up through G of Pk. So we're going to do the internal direct product of all of those, and then that is where each of those little P groups, its order is going to be Pi to the Mi for each I from 1 to k. Okay, so that is going to make up the whole group. And then we're going to use corollary 31.6 to write each of those little p groups as a direct product of cyclic groups. Okay, and then when we put all of that together, we're going to have G as an internal direct product of cyclic groups as well, and that is going to be isomorphic to an external direct product of cyclic groups. I don't remember how much we emphasized this back when we were talking about internal direct products and external direct products, but they are basically isomorphic to each other. So if all you care about is isomorphism, then you can switch back and forth between internal and external direct products. Okay, so that's kind of the basic overview of what we're going to see. So let's go ahead and get to it. So we have a definition here, definition 31.10. Let G be a finite abelian group of order n, and let P be a prime factor of n. The P primary component of G is the set G of P, which is equal to all of the elements A in G, where the order of A is P to the T for some non-negative integer T. So basically, G of P is just the set of all elements of G whose order is a power of P. And that's exactly what we were doing in the last activity where we had G of 2 and G of 3. All right, so let's do a little activity here, and I believe this is actually going to be our last activity for the class, where we're going to show that G of P is actually a subgroup of G. So go ahead and pause this video and try this activity, and then we'll go over it. Okay, so let's go over this. So part A, is E an element of G of P, the identity? So this is really easy. Yes, the order of E is 1. So if you have E and you take all the integer powers of E, you still just have E, so just one element. And that is P to the 0. So yes. And then the second part here is actually the hardest one. So is G of P closed? So let me try to justify why it is. So yes, so if we let A and B be elements of G of P, then we have to explain why A times B should be in there. So if A and B are in this G of P thing, then the order of A is P to the T, and the order of B is P to the S for some integers S and T. So that's what it means to be in that G of P thing. Then think about what happens if I multiply together A and B. So if I do, I don't know exactly what the order of AB is going to be. It's a little bit hard to say, but if I have AB and I raise it to P to the T times P to the S, then I can write that like this. So A to the P to the T, P to the S, B, P to the T, P to the S. Okay, and then I'm going to just rearrange this a little bit more. So this will be P to the T on the inside, and then P to the S on the outside. That's just rules of exponents there. And then this will be B, P to the S, and then P to the T. Okay, so then what's going to happen is, because I've raised A to its own order and I raised B to its own order, those are going to give me the identity. Okay, so this will just be E to the P to the S, and then E to the P to the T, and so that's just the identity. Okay, so since raising AB to a power of P gives us the identity, the order of P, or sorry, the order of AB must divide P to the S, P to the T. Okay, I don't remember which theorem that was. Maybe it was in like section 27 or something like that. But the order, if you're able to raise an element to a power and you get the identity, then the order of the element has to divide that power. So yeah, so the order of AB must divide P to the S, P to the T. So the order of AB is a power of P, because the only things that would divide P to the S, P to the T would also be powers of P. Okay, I hope that makes sense to you. The order, oops, totally lost track of what I'm writing. So the order of AB is also a power of P. Okay, hope that makes sense. So the last two are a little easier. So if the order of A is P to the T, then the order of A inverse is the exact same thing, it's just P to the T. Okay, so all the integer powers of A will actually be the exact same as all the integer powers of A inverse, because the integers include negative integers. So yes, and then finally, is it a subgroup? So we just showed that it is, so yeah. Okay, so this brings us to the last lemma and the last theorem. So the lemma here is a lemma because it supports the proof of this theorem, but we're not going to look at the proof because it's kind of long and technical, and I just want to like have a nice soft finish to the class without like a super long technical finishing proof. So the lemma here, if P is a prime factor of the order of G, then G of P is a subgroup of G whose order is a power of P. So actually we just proved that on the last slide, although I don't think we proved that the order is a power of P, but we proved that it's a subgroup. And then the theorem here, this is the big important theorem for the whole investigation, the fundamental theorem of finite abelian groups. Let G be a finite abelian group, then G is equal to G of P1 times G of P2 times ... up through G of Pk. So that is the internal direct product there of all those things. Where P1, P2, ... Pk are the distinct prime factors of the order of G. So the proof of this theorem, like I said, it's kind of long and technical. If you want to read it, it is in the textbook. I'm going to skip over it in this lecture here, but I will just show you an example of how we can apply this theorem, and this example will be extremely similar to your exam problem, the last exam problem. Okay, so let's look at example 31.15. To illustrate the fundamental theorem of finite abelian groups, we will find all abelian groups of order 360. So if G is such a group, then since 360, we can factor it into 2 cubed times 3 squared times 5. Then it follows that G, by that last theorem, is going to be equal to the internal direct product of G of 2, G of 3, and G of 5. So those are going to be some subgroups of G. We don't know exactly what they are, but their orders will be 8, 9, and 5 respectively. So by corollary 31.6, we know that since G of 2 is of order 2 cubed, which is 8, that means that G of 2 is going to be isomorphic to one of the following. So it'll either be isomorphic to Z8, the external direct product of Z4 and Z2, or the external direct product of Z2, Z2, and Z2. And then the same thing for G of 3. We know that has to be of order 9 because we have to make up 360, right? So that has to be isomorphic to either Z9 or the external direct product of Z3 and Z3. And then for G of 5, it's of order 5, so that can only be isomorphic to Z5. So when you put those things together, what you can do then is combine all of those different factors in all of the possible ways that you can combine them. So you have 3 choices of what you can take from this first line here, you have 2 choices of what you can take here, and then you have 1 choice for that last one. So you get 6 possibilities in total there. So half of them have Z9, and half of them have the external direct product of Z3 and Z3. And then 2 of them have Z8, 2 of them have external direct product of Z4 and Z2, and then 2 of them have external direct product of Z2, Z2, and Z2. And then they all have Z5. Yeah, so you just combine those in all the possible different ways, and yeah, that's it. So it's pretty interesting, and sorry that we didn't go over the proof for that, but hope that you got to see a lot of interesting and fun proofs in this class. Alright, that's it, folks. So that was the last lecture, and this is the last investigation. So please send me an email if you need any help with your homework or the test or even the exam. I'm not going to allow corrections on the exam, but I am going to help you make them on test 2 at least. So yeah, just send me an email if you need any help. We can do some Zoom sessions, or we can just email about stuff. I really am committed to making sure that everyone passes this class, so if you are not in contact with me, I'm probably just going to give you an incomplete. and then try to get in touch with you again over the summer or in the fall. So yeah, it's really been a pleasure teaching this class. I've really enjoyed it. I hope you guys have enjoyed it at least to some extent as well. Yeah, I hope to see you guys all next semester, or if you're graduating, then someday. Bye bye.